For our next problem, let's take a look at 6.28 from our textbook. So in this problem here, experiments have shown that for airflow at a temperature of T infinity is equal to 35 degrees Celsius and a velocity v1 equal to 100 meters per second, the rate of heat transfer from a turbine blade of characteristic length L1 equal to 0.15, now they actually give it to us in meters for this problem here, and surrounding surface temperature of T sub S1 is equal to 300 degrees Celsius is given to us as a value of Q1 of 1500 watts. So they want us to find what would be the heat transfer rate from a second turbine blade with a different characteristic length of 0.3 meters as compared to 0.15 meters, operating at a surface temperature of 400 degrees Celsius now as compared to 300 degrees Celsius, and a surrounding temperature is still the same of 35 degrees Celsius, but with a different velocity now of 50 meters per second rather than 100 meters per second. So the surface area of the blade may be assumed to be directly proportional to its characteristic length. So now that we've read through the problem statement for 6.28, what we can do next is write out all the variables, values, units, and how they apply to our problem. So that's what we've done here in our given section. So we know we have air temperature, T sub infinity, is equal to 35 degrees Celsius. And I've gone ahead and converted this to Kelvin right here, 308.15 Kelvin. We have V1, our velocity, is equal to 100 meters per second. We have length 1 in meters of 0.15 meters. And we have our surface temperature, TS1, equal to 300 degrees Celsius. And again, converted to Kelvin, it's 573.15 Kelvin. And we have our Q1 value given in the problem statement is 1500 watts. Now I've separated it out and done it for 2. Case 2 here, we have L2 is equal to 0.3 meters. Our surface temperature of the second turbine blade, TS2, is 400 degrees Celsius, or converted to Kelvin, 673.15 K. Our second velocity, V2, is 50 meters per second, so half of that of V1. And our surface area density is proportional to the characteristic length here. Now down below, what I've drawn here is drawn out our two different cases, a diagram for each. So we have our air, T infinity, V1. Case 1 here, here's our area, A1. Here's our surface temperature, TS1. Here's Q1 there, and our length, L1. Now over to the right, I've tried to proportionately draw out our case 2 here. Well, now L2, which again, if we go up top, L2 is 0.3, which is double that of L1, which is 0.15 meters. And we still have our air, T infinity, and our velocity, V2 here. Our area is now A2. And we now have this Q2 that we're going to solve for, and our surface temperature, T sub S2. So this is great that I have one page here where I clearly define case 1 and case 2, both of my schematics, all my variables, the actual numeric values, and the units that we're using for these. So this is a great page to reference back to as we're going through our solution. So now that we've had a chance to go through and write out all of our variable names and figure out what they're asking us to solve for in the problem for case 1 and for case 2, we next want to go and create all of our assumptions. So the first assumption we're going to make is that we're dealing with steady state conditions. We're also going to assume constant properties, and we're also going to have the assumption that the surface area A sub S is directly proportional to the characteristic length L. We're going to assume negligible radiation, so we're not dealing with any radiation terms here. We're also going to assume that the blade shapes are geometrically similar, even though their lengths and their sizes are different. So after we have our assumptions, the next step is to figure out our governing equation for the solution to this problem. So the governing equation we're going to start with here is the average Nusselt number. Now this comes from chapter 6 on page 401. We can see our general equation here. Our average Nusselt's number is equal to our H bar times L over K, which is a function of the Reynolds number and our PR number. So from this here, what we realize, if this is a function of Reynolds number, we're going to need to calculate the Reynolds number. So in order to calculate the Reynolds number, we're going to want to do it for both blades. So I'm going to stop here and switch over to a general equation for Reynolds number. So here's our governing equation that we're going to use to calculate our Reynolds number. So we have that RE is equal to, in this case we can go to the right hand side of the equation here, U is the velocity of the fluid with respect to the object in meters per second, L is the characteristic length in meters, and we have V on the bottom is our kinematic viscosity of the fluid in meters squared per second. So this is what we're going to use to calculate Reynolds number 1 and Reynolds number 2 for the two different shapes and sizes of the turbine blades. So now we take that equation for our Reynolds number and we apply it to both cases, because again we need to calculate the Reynolds number for both of the blades. So for blade 1, case 1, what we have here is Reynolds number 1, REL1, is equal to V1L1 over V1. Well, this is velocity, this is length, and this is viscosity. So now we know our velocity 1 for case 1 for blade 1 is 100 meters per second. Our length 1 is 0.15 meters, and our viscosity 1 we're just going to leave as V1 here. So this ends up being, for Reynolds number for 1 for blade 1, 15 meters per second over our viscosity 1. So we do the same thing for case 2 for the larger blade 2, V2L2 over V2, where this is second velocity, length, and viscosity here. So our second velocity is 50 meters per second. Our length is 0.3 meters, which is double that of 1. And we're going to leave this as V2 for our viscosity for blade 2 here. So we can do this here, and we can see that this is equal to this, and we know those must be equal. So from the relationship, we can determine that V1 is equal to V2. So therefore, Reynolds 1 and Reynolds 2 are equal to each other, and PR1 and PR2 are all equal to each other based upon this. So now that we've shown that the Reynolds numbers and the PR numbers are equal and constant, from case 1 to case 2, or blade 1 to blade 2, the next thing we want to do is go back to the Nusselt number here. So we go back to our key equation here, and now we can say that Nusselt number 1, average Nusselt number 1 is equal to average Nusselt number 2. So this is equal to, for case 1 for our blade 1, H1 average times L1 over K1, and for the second case, the larger blade, H2, L2, and K2. So we can set these equal to each other based upon this here. So we have H1 L1 over K1 is equal to H2 L2 over K2, where our K1 and K2 do not change between the two different cases, the two different blade sizes, so those remain constant. So now we can go back through and solve. So when we do this here, we can see the K's cancel out there, so we're left with H2 is equal to H1 times the ratio of L1 over L2. So now we recall, for our heat transfer equation here, Q is equal to our area times H times our temperature difference here. So for our specific case here, Q1 is equal to that area times H1 times T sub S1 minus T infinity there. And then what we can do is rearrange this equation here so that H1, if we solve this for H1, is equal to Q1 divided by the area times that temperature difference between TS1, or surface temperature in case 1, minus our ambient temperature for the air, T infinity there. Now with this relationship for H1, we can go back up in here to this relationship here in this equation and plug in terms of H1. So now we'll have our Q1A, TS1, and T infinity instead of our H1 there. So once we plug that relationship back up into the equation above, we end up with what we see here for a relationship here in the box, that our average H2 is equal to the ratio of our lengths, L1 over L2, times our Q1 divided by A1 times the temperature difference of our surface temperature, TS1, minus our surrounding ambient air temperature, T infinity. Now this here, we can then plug in, and we can use this relationship to calculate our Q2 value. So we plug this in down to this equation for Q2 here, which again we recall was Q2 is equal to our H bar 2 times A2 area times our temperature difference of the surface temperature 2 minus our ambient surrounding temperature T infinity of the air. Plug in this relationship here, and we have what we see here now of Q2 is equal to that ratio L1 over L2, so all this is coming from above here, of Q1 divided by A1 times TS1, our surface temperature, minus the temperature T infinity of our surroundings here. Now this is times the right hand side of this equation here, which is A2 times the surface temperature TS2 minus T infinity. We can rearrange and simplify this here. We can see we have our A2 over our A1, pull that out in front, and we have now our L1 over L2 ratio of our lengths times the ratio of our areas, A2 over A1, times our Q1 times our temperature difference for case 2 divided by our temperature difference for case 1, where this is our surface temperature minus our ambient temperature, surface temperature minus ambient temperature here for case 1. Then, with this equation here, we can plug in our known values. And this is why it's great that we have that first page of our solution, so we can reference back to that and plug in all those known values from one location directly into this here. We start to plug in, we know our L1 and L2, we can plug those in, and we start to plug in our A2 and A1 here, and then we realize that we have this assumption that we have a proportionality between A1 and L1 and A2 and L2, so if we were to do that, these would end up canceling out. Now, if you're not convinced of that from the assumption, I'd say go ahead, calculate your areas, plug it in, and prove this to yourself here. But I'm going to go ahead with our assumption and assume that. So we're just left with the right-hand side of the equation, which is our Q1 times our temperature difference when we plug in here of our TS2 is 400 degrees Celsius. Our T infinity is 35 degrees Celsius for both cases. And our TS1, our surface temperature for case 1, is 300 degrees Celsius. So now I can plug in for my Q1 value, which was given as 1,500 watts when I plug in here. So Q2 is equal to 1,500 watts times, when we do this guy out here, this is 365 degrees Celsius, 265 degrees Celsius. Plug those in, run this through our calculator. Q2 equals 2,066 watts.